In the interest of being on time, I think we better go ahead and get started. For those of you who were not here yesterday, my name is Sam Mukasa. I am president of the Geochemical Society, and I'm here to introduce the plenary speaker for the morning. You will recall that in the last several Goldschmidt conferences, we begin every morning with a plenary speaker, usually selected from the very distinguished group of individuals that we have as members of the society. Today's speaker is Mark Hirschmann, and I promised him that I wouldn't give him a very lengthy introduction and eat up all of his time. So I'm going to pick out a few remarks from his very illustrious career. And by the way, he did ask me not to use words like illustrious or distinguished, but I'm in charge here and I can use any word I want. Mark is the George and Oprah Gibson Professor of Earth and Planetary Sciences at the University of Minnesota. He has had a very distinguished career, and I hope it goes on for another many, many years, in experimental petrology. And his major contributions to experimental petrology have been on the origin of oceanic basalts and the role of water and carbon in the mantle and in magmatic processes in general. He has also been a major player in our understanding of the deep cycling of water and carbon in the Earth and in other terrestrial planets. Mark is a fellow of both the Mineralogical Society of America and also of the American Geophysical Union, and he is the 2011 recipient of the Bowen Award from the VGP section of the American Geophysical Union. This morning, Mark is going to speak to us about deep earth volatile cycles from ancient to modern. So please join me in welcoming Mark for his plenary session, for his plenary talk, I should say.
Okay, is this on? Thank you, Sam, for that very gracious introduction. And thank you all for waking up this morning. I know the pleasures of the evenings in Prague are great, so I'm sure it took considerable effort to get here. Okay, so my topic this morning is deep earth volatile cycles. Is this about the right volume? Is this okay? Okay. First, let me tell you what I mean by deep earth volatile cycles. There are a whole range of studies and integrated studies that many of us have been engaged in. Chiefly in the last 20 years, the deep earth water cycle has generated a lot of interest, but increasingly also carbon. And there are some really important aspects of this that I can say very simply, and that is that deep earth volatile cycles concern themselves, number one, with how much of the volatiles are on the surface and their influence on the surface, the existence of the oceans, the existence of the biosphere, and so forth, and how much of them are stored in the interior, in the mantle, or perhaps even the core, and the feedbacks between the presence of these volatiles in these different reservoirs. So there are many feedbacks, actually, but one of the most important, just to give you an example, would be if you imagine that the mantle contains a large amount of water, that would make the mantle convect more vigorously and also make melting more widespread. As a consequence, the flux of water out of the mantle would increase water to the oceans. So that is an example of a feedback. So what's the importance of deep earth volatile cycles? Everything. I don't think I'm really exaggerating with this list. There's actually one of these lists that I don't think is right, but I'm not going to tell you which one. All the others, I think, are actually quite applicable. But rather than summarizing all of these, I just want to emphasize the key link probably between deep earth volatile cycles and plate tectonics, because that's actually quite key. So, for example, let me go before I do that. There's a phrase that I often foist on people who are listening to me as I ramble on about deep earth volatile cycles, and this sort of summarizes why I think the importance of it. And that is that the oceans and the biosphere exist by permission of the mantle. If you want to take an extreme case, you can imagine, for example, that there were phases in the mantle in which water were very, very stable. In fact, we do know of hydrated silicates that are stable to quite high temperature. But if water were a compatible element in the mantle, there might not be any oceans. On the other hand, if you don't want to take that extreme an example, you can simply imagine if water was a little bit more stable in the mantle and more of it held in the mantle. And in fact, there are large quantities of water that are held in the mantle. But if it was a little bit more so, we would have perhaps much smaller oceans, or the opposite. Imagine an ocean that was, say, 8,000 meters deep and only the Himalayas and the Andes would be exposed. All of the Earth, climate, geology, and so forth would be very strongly impacted. Okay, the connection between deep earth volatile cycles and plate tectonics, there are a number of them, but just to highlight one, the very plate-like behavior associated with plate tectonics, in which we have a stiff lid and a great deal of deformation concentrated beneath that lid in a weak asthenosphere, is the characteristic of the dynamics of how the interior of our planet works. And that's intimately associated, first of all, with the presence of water, which has a factor of about 500 influence on the viscosity of the mantle through this depth profile, and perhaps also carbon, where some, including myself, have suggested is responsible for partial melting just beneath this region and perhaps the weakening of the asthenosphere. An important theme that I'm going to try to cover as I move through this in the time that I have is that this is the modern Earth, and that we have the ancient Earth, or the very early Earth, where a number of processes were happening associated with deep earth volatile cycles, and how this modern Earth is influenced or descends from the early Earth is very key to the story, I believe. Okay, so as I mentioned, the deep earth water cycle has been the subject of intense focus for at least a couple of decades, carbon perhaps the last 5 years and so forth. And the approach that I want to take today, although I'm chiefly interested in carbon, is to actually compare the two deep earth volatile cycles and ratio them, and to see what we can learn from that. And I think the constraints that we get from this ratioing are actually really quite powerful. This is just a summary slide that introduces you to this quantity that I'm going to be using, the hydrogen-carbon mass ratio of the different important reservoirs on the Earth. And in fact, I'm really only going to be focusing on the exosphere, which is pretty much everything, the oceans, the glaciers, and so forth, the continental crust, oceanic crust, everything above the MOHO, and then the mantle. Those are the two chief reservoirs that we want to talk about. So first we want to do a real simple inventory. The easiest one is how much water is in the exosphere, and that's really just the oceans. Add up everything else, rivers, streams, groundwater, amphibole and the oceanic, amphibole and continental crust and so forth. Doesn't add very much. You get a number that's very robust with a very, very small error. Carbon, before I talk about that, the other aspect of water that's interesting, of course, is that the inventory of water in the exosphere has not changed appreciably over a very long period of time. And that is something that people have studied. It's the problem often known as the continental freeboard problem. And perhaps going all the way back to the Hadean, we've had oceans that, if not exactly the same dimension and volume that they are today, then they are at least somewhat similar. So it's a very steady reservoir. The carbon surface reservoir is dominated by continental sediments. This is a model from Sleep and Zonley, but there are others who have come up with certain numbers. There's a little bit in the oceans, an appreciable amount in the oceanic crust tied up as alteration, chiefly calcite veins in altered basalt, but most of it is in continental sediments. We take different estimates of the total amount of carbon in the exosphere, 3 independent estimates, Sleep and Zonley, Hayes and Waldbauer, Holzhauer et al. 1989. We get basically the same number, and we generate this ratio. The hydrogen-carbon ratio of the exosphere is approximately 2. This is, surprisingly, a really strong number in terms of our understanding of Earth processes. It's a surprisingly large number compared, for example, to that of meteorites. And perhaps more importantly, it's a very large number compared to the deep reservoirs, or at least compared to the mantle. So if we try to extract the hydrogen-carbon ratio of the mantle based on basalts, and this is not an easy task, there have been many efforts and degassing gets in the way, but if one looks at all the serious efforts, one gets numbers perhaps an order of magnitude lower than the exosphere, but usually a factor of 3 or 4 lower than the exosphere. Key point, the hydrogen-carbon ratio of the exosphere is very high compared to the mantle. There has at some point been a very strong fractionation, and that fractionation actually is not very well understood, and I'm going to go over some ideas as to how to explain it. I'm not happy with any of them. I ask all of you to drop what you're doing and to come up with a better model than what I have, or a better explanation. Okay, so how can this be? Volcanic outgassing probably is not the answer. Carbon leaves the mantle more effectively than water. Water is partially retained, so it's not possible to generate a high hydrogen-carbon ratio in the exosphere by extracting carbon preferentially from hydrogen during melting, and I'll demonstrate that for you in a moment. Normally, we would say, at least under most normal conditions, that escape to space also does the opposite. Hydrogen escapes preferentially to carbon. If there's any fractionation at all, also can't generate a high hydrogen-carbon exosphere ratio. And then I'll cover these in a moment. Okay, so if we understand the influence of oxidized carbon, CO2, in the mantle, and also the influence of water in the mantle, we find that they're both incompatible during partial melting. They're both extracted, and therefore they're not fractionated very much. Or if they are fractionated, the fractionation is such that CO2 incites melting at a greater depth than that of water, and as a consequence, the carbon is extracted preferentially from the mantle as compared to water, if at all. So during partial melting of the mantle, we would expect greater fluxes of carbon to go to the exosphere compared to hydrogen, and we would expect generating an exosphere with a low hydrogen-carbon ratio, the opposite of what we observe. So this is not the explanation. This would not be the case if carbon were to stay in the mantle during melting, and this could be the case if carbon were in a refractory phase, such as graphite. And so one can imagine a more reduced mantle in which water was easily extracted and carbon remained in graphite. But at least in the modern mantle, the measurements of the oxidation state of the mantle as evidenced by mid-ocean ridge basalts, I should say we don't have nearly such good constraints on oceanic island basalts, but at least for the largest fluxes coming out of the ridges, they're more oxidized than that required for the stability of graphite. And so we don't have this refractory carbon staying in the mantle today. People who have looked at the history of the oxidation state of the mantle using trace element proxies such as chromium, which is what I'm showing here from a study of John Delano a number of years ago, have concluded that the modern Earth gives patterns like this, a little bit more oxidized than FMQ, quartz phayolite magnetite, and that going back all the way through time to older volcanics, one sees no secular variation. And Dante Conneal has also looked at this with vanadium. There's really no evidence that this condition was realized at least in the last 4 billion years, although I'm sure there's room for lots more work to try to scope out whether or not that is the case. So, volcanic outgassing has the opposite effect. Loss of volatiles to space, at least under normal circumstances, has the opposite effect. Preferential seduction of carbon. When I first got into this problem, this is what I thought the answer was, and in fact I gave talks a number of places arguing that this was the case, and now I'm going to tell you that I don't think it's the case, but let's at least go through it. Okay, so we have oceanic crust that gets carbonated on the seafloor. We have calcite veins, and that oceanic crust is then subducted. And during metamorphic devolatilization, it's fairly well known that the calcite does not get removed and that the calcite remains. But ultimately, there's another way that the carbon can be removed from subducted crust, and that is by melting. And a number of years ago, Raj Dasgupta, who at that time was a graduate student working with me, did a study of the solidus of carbonated eclogite. This would be the temperature-pressure trajectory that's required to extract carbon from subducting crust during during its downward path. We compare that to the various different temperature depth paths of subduction in the modern Earth, and concluded that for the most part, this solidus is too high, which is to say that carbonated oceanic crust should go down into the mantle and stay there for long periods of time. That's great. So now we can put large amounts of carbon into the mantle and generate, as a consequence, a high hydrogen-carbon reservoir in the surface. However, this just illustrates that. As I argued before, the water reservoir on the surface is fairly constant through time, the exosphere water. If carbon is being subducted, so the surface reservoir is being reduced with time, the hydrogen-carbon ratio of the exosphere develops some high ratio compared to the original, and we get the fractionation that we observe. Great, okay. But, like I said, I don't think it's right. Why not? First of all, these are modern subduction temperature depth paths. They're not what have persisted through geologic time. And if we look in the geologic record, we see evidence that, that these have not persisted, or that these are relatively recent phenomena, is I guess what I mean, because, of course, the Earth was hotter in the past. So this is a compilation from Mike Brown from a number of years ago, going back in time to the metamorphic gradient, which is in degrees per GPa. It's basically the slope on a trajectory going down this way. And what we see is that the modern subduction geotherms, the so-called blue schist geotherms, are restricted really to about the last billion years. And that before that, the temperatures that were attained as a function of depth were much, much greater. And these were so-called, what Mike Brown calls these eclogite high-pressure granulite terrains. If we plot those on basically the same diagram that I just showed you, they plot over here, hotter than the modern slab, and importantly, inevitably intersect the melting relationships of carbonated eclogite based on our own experiments and also that of pretty much any other group that's looked at it. And so before a billion years, it was extremely difficult to subduct oxidized carbon. And so if that has occurred on Earth, it's only occurred for the last billion years, or at least been plentiful in the last billion years, that flux. The second reason that I've become skeptical of this idea has to do with just looking at the sedimentary record and what people who care about storage of carbon in sediments have thought for a very long time, and that is the opposite of what would be required for subduction being the explanation. That is to say that most people think that the amount of carbon stored in continental sediments has grown with time, not diminished. And the evidence for this is looking at stratigraphic sections as a function of age. And what we see is that carbonates, limestones, and dolomites are only abundant in sedimentary sections in the Phanerozoic and the recent Proterozoic, and that if one goes back into the early Proterozoic or the Archean, they're quite scarce. Now, you can argue that this is a function of preservation, but it's not the abundance of dolomites or carbonates, it's the abundance of dolomites or carbonates as compared to other kinds of sediments, suggesting that with time, there has been increased storage of carbon on the continents, not the opposite, like this. So if we have water really not changing very much, it can change by 20% if you like. That's a huge change, but it's not a large change in terms of these ratios. If you have the carbon reservoir increasing with time, then what you would expect is that you would develop through time not a large hydrogen-carbon ratio on the surface, but the opposite. This really simple observation, how much hydrogen and how much carbon are on the surface of the Earth, is a really strong constraint on the operation of these large-scale processes through geologic time. Okay, I'm not going to talk about this in great detail, but it comes up every time I give a version of this talk. So I will point out that if we look at the carbon isotope record through time, we don't see a significant evidence for secular variation over long periods of time, and that too would be difficult to reconcile with an explanation of large-scale subduction of carbonates through geologic time. Perhaps one can make it work, but it would at least be a challenge. So, I've already eliminated these. I used to like this, but it has fallen out of favor. And then there's not much left in terms of modern processes. If it's not volcanic exhalations of water and carbon creating this fractionation, or recycling creating this fractionation. One is forced into the rather radical and somewhat amazing possibility that the hydrogen-carbon ratio of the modern Earth is a remnant of processes that go all the way back to 4+ billion years ago. And there are several of these that are potentially responsible. So again, to take Chris Ballantyne's great cartoon, what I'm suggesting is the possibility that this Earth here has given us the template of storage of water and carbon, not just on the surface, but that also means the relative storage in the mantle. And remember, the dynamics of the mantle and the dynamics of plate tectonics are in part, if not dictated, strongly influenced by these relative inventories. And so the suggestion, perhaps, is that the dynamics of our planet have been imprinted by these early processes. We don't know when plate tectonics began. We also don't know, although we're trying to figure out, the history of the deep Earth volatile cycles. But if it's a chicken and egg, it's possible that the deep Earth volatile cycles and their history very early in the Earth, in fact, were necessary for the way that the Earth operates today. Okay, so how about these early processes? One possibility is that in contrast to normal atmospheric escape, preferential loss of hydrogen, that there may have been an episode of catastrophic loss of a thick carbon dioxide atmosphere, something like an atmosphere of Venus today, 100 bars of CO2, catastrophically lost without losing a large amount of water. And in fact, there's a very simple mechanism for that, and that would be a giant impact. If we had a planet or a protoplanet that consisted of a CO2 atmosphere but was cool enough so that the water had condensed into an ocean prior to a giant impact, then what simulations show is that the ground accelerations associated with that could be great enough to create large amounts of atmospheric loss without appreciable loss of the oceans. And this here is the ground acceleration associated with a Mars-sized impactor, perhaps the moon-forming impact, work of Genda and Abe, which would lose large amounts of a thick CO2 atmosphere without appreciably ejecting any of the oceans. That could do it. However, it would create a reservoir, a remnant reservoir that was very rich in water and very poor in CO2. However, of course, the giant impact also has other consequences, and that is formation of a magma ocean. So anything that occurs prior to a magma ocean and the fractionation associated with it would then have to be processed through the magma ocean. And in my remaining time, I'm going to talk about magma oceans for the most part. So what is the influence on hydrogen-carbon fractionation for magma oceans? The assumption that I'm going on is that magma oceans persist for long enough such that they equilibrate chemically with their overlying atmosphere. So we can determine the solubility of water and CO2 in underlying magma ocean according to the atmospheric pressure of water or of those volatiles. And what we see, of course, is that water is much, much more soluble in magmas than CO2. So however much water and CO2 are present at the onset of a magma ocean, most of the water, or more of the water, rather, gets dissolved in the magma ocean than CO2, and you end up with an atmosphere that, I'm sorry to say, has a low hydrogen-carbon ratio compared to that of your molten mantle. Again, the opposite of what we observe today. Even worse, if one dissolves water preferentially into the magma ocean, once the mantle crystallizes, of course, the mantle silicates take small amounts of water, the nominally anhydrous silicates, olivine, wadsleyite, etc. They don't take appreciable carbon, and one ends up with a reservoir that has a high hydrogen-carbon ratio and a remnant atmosphere with a low hydrogen-carbon ratio. Again, this is a bit of a problem for what we observe today. We need something else. Something that was suggested about 10 years ago by Kevin Zonley and Norm Sleep was that after this all happens, that there's this really spectacular episode after crystallization of the magma ocean, formation of a very thick CO2 and water-rich greenhouse atmosphere, that there is this catastrophic loss of the surface reservoir of carbon, and that's what this plot is, how much carbon there was on the surface through time. And their reasoning is that their that the surface of the Earth after the giant impact basically consisted of a bunch of basaltic or even ultramafic glass beads, remnants of the giant impact and other impacts and so on, and that these glass beads very, very actively react with the CO2 in a weathering process, and that somehow, through a tectonic process that we do not understand, in a very hot Earth, this material gets put into the mantle. If we can imagine such a process, our problem is solved. So this would be some sort of subduction catastrophe early in the history of the Earth that would put virtually all of Earth's carbon into the mantle, and then since then, outgassing and buildup of the continental carbon reservoir. Okay, possible, but let's talk about another one that I like more. Degassing of a reduced mantle. Imagine, if you will, a large amount of carbon dioxide in the atmosphere dissolving into a magma ocean in which the solubility here is much larger than the concentration of carbon here that can be tolerated without precipitation of a carbon-rich phase, such as graphite, diamond, carbide, or an alloy. That would create a carbon pump. Convection would take carbon-rich magma down into depth, precipitate the carbon, create a carbon-poor magma, which would come up, re-equilibrate with the atmosphere, and just pump the carbon into the mantle. Is this possible? Yes, this is possible if. It is possible if the surface conditions in the magma ocean are comparatively oxidized and the deep conditions in the magma ocean are comparatively reduced, because the amount of carbon that can be dissolved in the magma under reduced conditions is very, very small. Right? So graphite precipitation, or in fact diamond precipitation, would happen in a magma that just had a few parts per million carbon under these conditions. This could do it. Is this obtained? Well, this is actually an area of current research of my group, and we're beginning to work on it, so I don't actually have results to show you, but I have some speculations and also some earlier results from other people. The idea would be that a magma ocean would be very well mixed. Of course, it would have metal at the bottom, and this very well mixed magma ocean would have a certain amount of ferric iron as compared to total iron that would be constant. Right? That constant amount of ferric iron, or ratio of ferric iron to ferrous iron, would not give continuous conditions, continuous is the wrong word, would not give the same conditions at depth as the interior, because the self-compression of ferric and ferrous iron would impose different oxidation states at the surface and at depth. What do we know about that? We have experiments, Kress and Carmichael, from a fairly famous work 20 years ago, a more recent work from O'Neill et al., suggesting that self-compression of a magma, of an iron-bearing magma, creates conditions where the ferric-ferrous ratio at fixed oxygen fugacity relative to an oxygen buffer diminishes, like this. So if one were at some particular condition at depth, and one decompressed at constant ferric-ferrous ratio, because the magma was well mixed, one would find that the conditions became more reduced near the surface. This is the opposite of what we need. Right? So this would be a very well mixed magma that has a constant ferric iron to ferrous iron ratio, is more reduced at the surface, more oxidized at depth, but of course that more oxidized is in equilibrium with iron metal. The conditions here would be even more reduced. We wouldn't have any CO2 in the atmosphere at all. It would be all methane, no water. It would all be hydrogen. And my carbon pump that I just proposed to you would not work. Interestingly, this change with self-compression, which is for molten mantle, what I just showed you, more oxidized with depth, is the direct opposite of what we believe to be true for solid mantle. There's a large amount of evidence that suggests that self-compression of an isochemical solid mantle creates conditions that are comparatively oxidized at the surface and more reduced at depth. And this is both from evidence from xenoliths, from thermodynamic calculations, from experiments, and so forth. What I suggest to you is that what we know about magmas that have the opposite effect of to solid rocks only applies at low pressure, and that at high pressure, magmas actually mimic that of solid mantle, and that this trend reverses, and that this could create the carbon pump that we need to explain all these wonderful things, most importantly, the modern day high hydrogen carbon ratio of the mantle. Okay, why do I say this? This is actually simulations of silicate melts that have no iron in them at all, magnesium silicate, but what they show, and what has been very well documented, is that the coordination changes in magmas as a function of pressure mimic that of the underlying minerals. The higher coordination states are obtained with greater pressure. And furthermore, it is the higher coordination states that are obtained in the minerals that actually stabilize ferric iron in the solid mantle. And this is demonstrated here by this experimental study of Rohrbach et al. Garnet coexisting with iron metal with increasing pressure has a greater majorite component, higher coordination species, and as that occurs, that's the reason for the reduction as a function of depth for the solid mantle. If the same occurs at high pressure in molten mantle, then we would have not this, which is what I've shown you is based on low pressure experiments, but this. At low pressure, the same trend, but as the magmas take on higher coordination states of the cations, a reverse of this. If this is obtained, then the carbon pump works. Then it's forced to work. Solubility of CO2 from the magma ocean into the magma delivers comparatively carbon-rich magma at depth, which then precipitates as, actually I don't know what phase, but a carbon-rich reduced phase. Let's call it diamond, because that would be fun. And as a consequence, the crystallization of the magma ocean would leave a mantle that was carbon-rich compared to hydrogen and have a fairly low hydrogen-carbon ratio, and a remnant atmosphere that had a high hydrogen-carbon ratio. Okay, because I have a couple more minutes, I just want to digress to point out that although what I'm trying to explain is partitioning between the early atmosphere and the mantle and how that may have impacted the modern mantle, there's another very important consequence of this, and that is the earliest atmosphere. The history of this, as I think many of you know, is that, probably all of you know, is that it was first proposed based on analogy to Jupiter, that the earliest atmosphere was very reduced, rich in hydrogen and methane, very conducive to prebiotic chemistry, and so on. This idea fell out of fashion for a host of reasons, and it was then widely believed that the earliest atmosphere was comparatively oxidized, composed of water and CO2. More recently, the reduced, I don't want to say primordial, early atmosphere has come back with the idea that the atmosphere is actually delivered by degassing of planetesimals with compositions like chondritic meteorites, and that degassing of those chondritic meteorites actually creates a host of reduced species, not so different from the Miller and Urey atmosphere. What I want to point out to you is that it doesn't really matter what's delivered to the Earth. What matters is that during the magma ocean stage, the atmosphere is forced to equilibrate with the magma ocean. The magma ocean is a much, much larger redox reservoir than the atmosphere, and that whatever redox state the magma ocean sets at the surface will set the composition of the speciation of the atmosphere. And if this is the case, as I've shown you based on low pressure experiments, then metal here means even more reduced, even more reduced conditions here, and we have a reduced early atmosphere, conducive to prebiotic chemistry. And if this is the case, the opposite may be so, and the earliest atmosphere may in fact have been chiefly CO2 and water. Okay, so I'm not going to read my conclusions to you, but I hope in return for waking up early this morning, you come away with a few important concepts. One is that the deep earth volatile cycles are intrinsically related to the dynamics of the planet and to very many different kinds of geologic, geochemical, and geophysical phenomena. The second is that the hydrogen-carbon ratio of the surface, something that is very easy to measure with relatively high precision, at least based on from a geochemist's point of view, and certainly from a geophysicist's point of view, that is a very strong constraint on what actually has occurred on Earth through time with the deep earth volatile cycles, and it's actually very difficult to explain. The high hydrogen-carbon ratio of the surface reservoir compared to that of the interior is a challenge to our understanding of how these operate. My attempts to understand this based on modern processes, to my satisfaction at the moment, have failed, and I have therefore been looking at early Earth processes to try to understand this, such as the carbon pump in a magma ocean. And it may well be, whether I am right or wrong about the carbon pump, that in fact the reservoirs that we see today on the surface and and compared to that of the interior are a remnant of the earliest Earth. Thank you.
I'm sure that Mark would be very happy to entertain a couple questions. We have time for this.
Odette? Loud. Odette asks, would there be any consequences for carbon isotope budgets? Certainly the long-term cycling of the modern Earth with subduction and degassing, one might think should, and people have worried about this and come to some ad hoc models about some balance between subduction of oxidized carbon and reduced carbon to try to keep that budget from, the isotope budget from going off of what we actually observe. Whether or not there are consequences for what I'm suggesting, the high temperature fractionation, I don't think we have the data.
You seem to have ridiculed the possibility that there was early subduction of CO2 back into the mantle, and then that subduction process probably continued for a very long time in the Earth's history. Of course, since we proposed that, so I would like to know how you simply brushed away that very easily.
Yoshua, I'm sorry, I don't understand the question. What is it that I need to explain away?
You didn't like the subduction of carbon back into the mantle.
Right, right. The two observations that I think challenge that, and we could perhaps find ways around them, is the relatively high temperature of metamorphic geotherms that are thought to be subduction geotherms past 1 billion years, which are too hot to allow deep carbon subduction. And also the sedimentary record, which seems to suggest that the carbon reservoir on the surface has been growing, not diminishing. Oh, okay.
Hello. The lack of carbonate deposition during the Archean was, I think, and I'm fairly well able to show that the ocean water was very low pH, and also most of the cratons, except the active parts at any one moment, were below sea level, so carbonate deposition really wasn't on until after the oxidation event at 2.3 or thereabouts. And that's why at that time you get a sudden flush of carbonate deposition at 2.2.
Right, and what that means is that if there was a large amount of remnant carbon from very early processes, it was stored in some other mode, not as continental sediments or not as sediments, but some other way that in fact, I have trouble imagining.
I think it was stored in the ocean. The CO2 was stored in the ocean.
Yeah, if you look at the numbers, you would need to have an ocean that was about 20 or 30 weight % CO2. I don't think we had soda ocean.
Can we rule out the lack of carbon initially in the Earth to begin with, not have to store it at all?
Can we rule out?
Well, we know the Earth is depleted in sulfur, for example, relative to chondritic.
Something that I took out of the talk in the interests of time was a comparison between these HC ratios that I'm looking at in the modern reservoirs and cosmochemical HC ratios. And what if I had shown that, what you would see is that the surface reservoir, the exosphere, is very high compared to that of everything, including carbonaceous chondrites, and that the bulk silicate Earth is perhaps a little high compared to that. But there are lots of ways to explain that, whether it be loss of a massive CO2 atmosphere, storage of carbon in the core, and so on. So it's a little bit difficult to get back to the original building blocks. So what I have focused on instead is the fractionation that we can observe between these two reservoirs that are pretty near at hand, the surface reservoir and that of the mantle.
There may be evidence in meteorites for this kind of carbon pump cycling occurring in primitive parent bodies in the early solar system, probably smaller than the Earth, perhaps.
Perhaps.
In the aerolites.
I think we need to move on. Or are there more questions? Any more questions?
Okay, one more question, perhaps? Otherwise, I'll just go ahead and thank Mark one more time.